Hello and welcome to NPTEL MOOC on fiber optic communication systems and techniques. In this module, we will look at semiconductor optical amplifiers, which is one of the optical amplifier that is used in fiber optic communications and fiber optics signal processing fields. Now, the reason I am discussing semiconductor optical amplifiers is because you can convert a laser, semiconductor laser, into a semiconductor optical amplifier by removing the optical feedback or by requiring the optical feedback be very low. Okay. Of course, that is what differentiates between any optical amplifier or in general any amplifier with a laser being the oscillator. So, when there is a feedback, then this feedback will be sufficient for the device to generate self-sustained oscillations in the steady state, whereas when you remove the feedback or you adjust the feedback such that the feedback is not important, then you won't be able to build on the oscillations, and what you will actually have end up with having is a optical amplifier. Much of the working that we look for in the semiconductor optical amplifier, the principles of working is the same as that of the semiconductor laser. You will have an inversion layer where there will be stimulated emission, but this stimulated emission will be brought about by the externally applied signals. The cavity will still be there in some form of the other, okay, but the cavity reflectivities are usually kept very low so as to obtain a broadband lasing, broadband amplification rather than lasing, and all the other principles of laser also remain. So, you have to have a heterostructure laser or have a heterostructure material, and then you have to have an injection by way of applying an appropriate current, forward biasing the junction, for example. All that thing that we discussed will still be there. Okay. So, then what is the different features of semiconductor optical amplifiers is what we want to look at. Okay. Now, any amplifier, the function of that any amplifier would be very simple. So, you send in certain light here which has an electric field E in, then the output would be ideally square root G times E in. I am using square root G because G or gain is usually referred to the power quantity and not to the electric field. Okay. So, G is usually what is called as the power gain and not to the electric field. So, for electric field you simply square up the power gain, and therefore, you will be obtaining what is the field gain. Okay. Of course, if it was an ideal amplifier, this is what it would have done, but most physical amplifiers also add a certain amount of noise to the output. Okay. This is kind of amplified spontaneous emission noise that is added from the semiconductor material itself, and the amount of noise that goes into the band depends on the bandwidth of the input signal itself. Usually the gain is broadband, and when you send in light at a particular frequency or with a certain bandwidth around a particular carrier frequency, the in-band noise is determined by what is the bandwidth of the input signal. So, this is what one would expect from an ideal amplifier and what one would expect from a non-ideal amplifier. Okay. But how exactly is this created? Well, if you look at the structure of a semiconductor optical amplifier, most structures fall into two types. One is called as the FP cavity type structure, okay, wherein the lasing material is actually kept, or the active medium is actually kept in between two mirrors. Okay. These mirrors can be physical mirrors or they can be made in the form of a grating, whatever way that you make them, but they essentially are, their properties is that of a mirror, and then they have reflection coefficients R. Okay. If R is close to unity, then what would happen? As the mode starts to propagate, it would move and then it would get fed back here. Almost all of the optical mode would be fed back, which would then pass through the SOA material in between or the gain medium in between and induce more stimulated emission, and then when it comes back to the first medium, it will again be reflected if R is very close to 1. And this process continues to happen, thereby you will essentially have a nice laser, but that is not what you want. What you want is not a laser, what you want is an amplifier. Therefore, you keep this R values to be quite small. Okay. So, most R values are just about 0.1, and as one tries to make this R value even less than that, okay, but most materials, unless they are specifically made, then they will have reflectivity of about 0.1 or slight or less than 0.1. Okay. So, that most of the light is not getting reflected, most of the light is actually coming out of the cavity, in the sense that when you launch a probe light at a certain wavelength, then what you would get at the output is an amplified version is with some amount of noise, but almost faithful replication as that of the input. Okay. So, this is what you would have. Of course, how do you inject here? What is the pumping mechanism? This is the injection current that you need to supply, and this is a PN junction. Therefore, you take this SOA and then forward bias this junction, and then essentially send in some input and you obtain the output. But because this SOA material is kept in the cavity, there are differences in the way the gain actually comes out. Okay. So, what we are now going to do is not to go back to the semiconductor basics. We have already looked at that theory enough. Whatever we have said about lasers, most of that also applies to the semiconductor optical amplifiers also. But what I am interested is to look at the amplifier gain as a function of frequency omega. Do you first of all agree that this will be frequency dependent? Well, it will be frequency dependent, because you have to agree, because the SOA material itself is a frequency dependent material. Remember, all lasers have a certain line shape. This line shape will be either in the form of a Lorentzian or in the form of a Gaussian line shape. This is of course a function of frequency omega. You do not have any lasers which generate, or any gain medium which has a delta like spectrum. So, most of them actually have a certain variation, and you would expect that the gain of this FPA also to be something like this with respect to omega, with a maximum gain which we will call as, this is FPA max, and a minimum gain that would occur at the tail, which we would call as G min FPA. This is what you would expect. So, this is what I would actually expect from this one, but what in reality you get is a different thing. So, you will actually get something like this. So, you notice that you have an overall Gaussian type function. I did not write the other this one correctly, but essentially this is a Gaussian type function. Okay. But there are these regions where the gain is at a minimum level. So, there are these blanks in between, and there are these peaks, multiple peaks within the gain spectrum of the amplifier material. This is a characteristic of the cavity. So, if you assume that the cavity has a certain length L, then the spacing between these two peaks is about C by NL or maybe C by 2 NL. Okay. You can fit a half length or something, and the idea is essentially the same. So, you have a cavity which would serve to have standing modes rather than the travelling modes. They are actually the standing modes, and only certain standing modes that satisfy the boundary conditions will be sustained by the cavity. And because you have now have some sort of a periodicity, right, periodicity in the form of wave going here, coming back, and then moving again in the same direction. So, one round trip propagation can be considered to be a spatial thing. Okay. And because periodicity is there in one domain, there has to be discreteness in the other domain, and this is precisely the discreteness that you are actually seeing. And this spacing between the gain medium is called as free spectral range. Okay. To increase the free spectral range, to increase the spacing between the peaks, you want to make L to be as large as possible. Of course, there are practical limitations as to how long you can make these devices. Therefore, you have to live with the fact that the gain spectrum is discrete and actually shows up multiple peaks. Okay. Of course, within these peaks, the peaks themselves are reasonably broad, so that most of the wavelengths can be fit into it, but not every wavelength in the operating fiber optic communication system can be fit into one of those two peaks. If you are interested in the expression for what would be that gain as a function of frequency, you may actually see that this will be given by Gs of omega, where Gs of omega is the line shape function of the basic lasing material, whatever the laser active gain material that you have used, times 1 minus R Gs of omega square plus 4 R Gs of omega sine square omega minus omega 0 into n by V. Okay. Where V of course is given by C by n is the phase velocity. Okay. Because sine square is an oscillatory function, the overall gain will be an oscillatory function. Omega 0 is called as the design frequency. it is the frequency at which the gain will be maximum. Okay. So, if you are making a, or if you are fabricating a semiconductor optical amplifier and you want to maximize the gain at a particular wavelength, you choose that wavelength to be omega 0 or corresponding to the frequency omega 0, and you get a maximum gain. What is the maximum gain? Well, when omega is equal to omega naught, you have gs omega naught 1 minus r whole square divided by 1 minus r gs omega naught square, because you will get a maximum gain when the sine square term goes to 0 up there. Sine doesn't, well, this term could have gone to negative, but because it is a sine square term, it will not go to negative, and gs of course is always a positive quantity because this is a gain of the basic material, or sometimes also called as single pass gain. Okay, that is the gain that the optical medium will undergo when it passes through the semiconductor optical amplifier of length L. Okay. So, this is what you would get, and if you now look at different values of R, okay, you can then change the different, I mean you will get different values of gain. Okay. That is something that you can easily observe from this equation, which I will not bother you too much, but notice that the gain can actually go all the way to infinity, right. So, it can go to infinity when R gs omega naught at that particular frequency approaches 1, right. So, when the denominator goes off to 0, then the gain goes to infinity, and essentially you would have obtained, instead of an amplifier, you would have obtained a laser. Therefore, this condition is not suitable for us, and R gs would always be kept less than 1. In fact, it should be kept much less than 1. That is the first observation. The second observation is, if you look at the ratio of the maximum gain to the minimum gain, right. I leave you to find out what is the minimum value of the gain, or at least show that this minimum value of the gain is given by gs 1 minus r square divided by 1 minus r gs whole square plus 4 r gs, and it will happen at those frequencies where this sine square term goes off to 1. Okay. So, when the sine square term goes to 1, you can find out what frequencies does that condition hold, and for those conditions you will actually have a minimum value of G or the gain. The maximum value anyway we have written, it is gs 1 minus r square in the numerator divided by 1 minus r gs in the denominator. So, what you can see that you can cancel off these two, and you get 1 minus r gs whole square plus 4 r gs divided by 1 minus r gs whole square. Okay. You can of course take this 1 minus r gs whole square as a common thing, and then call this one as delta G. Delta G stands for the gain ripple. Okay. Gain ripple means certain frequencies or certain bands will have a larger gain and certain bands will have a minimum gain. So, what is the difference between the max and the min gain in terms of, usually in terms of the ratio, would be about 1 minus r gs whole square 1 plus 4 r gs divided by 1 minus r gs whole square. Okay. So, you can, if you wish, simplify this further, and you can calculate certain numbers which are actually going to be interesting. Suppose I take gs equal to 3 and I take r equals 0.32. Okay. So, what would be the product r gs? This would definitely be less than 1, because the product is actually about point. So, this is 3 times, right. So, 3 2s are 6, 3 3s are 9. So, you are very close, but you are not exactly close. But if you look at what is the gain, you know, the maximum gain for this particular case, the maximum gain would actually be about 867 in the linear scale, or about 30 dB approximately in the dB scale. Okay. This is a huge value, whereas the minimum gain for the same condition would actually be even less than 1. In fact, it would be a loss if you choose this particular value, and in fact it would be less than about 0.36, right. In the, if you look at the difference between these two, which would of course be less than 0 dB, the gain ripple is about 30 dB. So, if you have signals of two different wavelengths, so, or two different frequencies omega 1 and omega 2, if omega 1 and omega 2 happen to fall into this unfortunate situation that this is your omega 1 and this one is, or rather this one is omega 2. Okay. So, if this is omega 2, then you can see that omega 1 channel will experience an extremely large gain, omega 2 channel will experience almost no gain, or in fact it experiences loss. And when you had initially same power, but after passing through the SOA, now you have a large power here and almost no power in omega 2. So therefore, this is not a very good mechanism, or this is not very good value to choose, because you are then essentially creating unequal gain distribution in the multi-channel system, which is not at all good, because you expect all the channels to be amplified with the same level, not with different levels. How do I ensure that that is happening? So the way to ensure that one would be to further reduce RGS. Consider taking the single pass gain to be GS equal to 2 while keeping R to be the same 0.32. In this case, the product is about 0.64, which is less than 1. Okay, the difference is not too much. You would think you have 0.96 in one case, you have 0.64 in the other case, but it turns out that the maximum gain, again you have to verify that these numbers are correct. Okay, please do that one. The maximum gain is about 8.5 dB. Okay, so this is 8.5 dB. The minimum gain is still quite less than 1, so the minimum gain is just about 0.32, but now you see that the gain ripple is down to just about 8 dB. So this is the ripple that you actually get, which is much smaller than this one. So this is actually very important, but if you can reduce R further, which is what normally we do, you can keep the single pass gain high but reduce R further, which is entirely possible by the technology that we have today. Okay, so what you would essentially convert, or what you would essentially do, is to minimize this gain ripple. Okay, so but still the gain ripple would be present if you were to use an FP cavity type filters. Okay, we are also interested in the bandwidth of these devices. So if you actually look at the bandwidth, you can actually find out what would be the bandwidth of this one, but the bandwidth actually depends on how the wave shape or the line shape itself goes, or the single pass gain itself goes, and the single pass gain itself is given by e to the power or exponential of gamma g of omega comma p minus alpha times L, where alpha corresponds to the resonators or the reflection losses that would happen in the cavity. Gamma corresponds to confinement, which is kind of an overlap between the optical mode and the cavity design itself, and most importantly this is the gain medium frequency dependence. So this is where you are actually getting all of your gain differences. Of course, for this to actually be positive, gamma g of omega comma p at every frequency and for every power must be greater than alpha, so that overall you will have gain and not absorption or loss. Okay, so these conditions are to be satisfied for any type of amplifiers or a gain, but this is what you would actually have. And further, this g of omega comma p itself is given by a frequency independent gain function and divided by this term in the denominator, and this term in the denominator where we have written p sat is called the saturation power. At the saturation power, what will happen? For p much less than p sat, the denominator can be approximated to 1 and the gain would be essentially independent of the power. Okay, so and it would have some sort of a variation that is dependent on the gain shape function g of omega itself. But if you were to plot the gain as a function, overall gain, let us say, as a function of the input power or the probe power or the input channel power, then for p less than saturation value, the gain is almost 1, but at this point actually starts to drop and then eventually drops off further. So the value of the gain at the saturation value when p equals p sat is just about g by 2. Okay, so that would essentially correspond to the bandwidth in terms of the saturation power. It is kind of quite difficult to obtain proper equation or an understanding between gain and p, because it is a complicated process that takes place, but approximate equations have been derived. So approximately GS depends on the input power in this particular manner. It's a transcendental equation, so you will have to solve this equation numerically most of the times, otherwise you won't be able to find, because there is GS on the right hand side, GS on the left hand side as well. Okay, again please note that there are many competing processes that are happening in the semiconductor optical amplifier. The actual gain depends on cavity design, reflectivities, the stray light that enters into it, the packaging, all those things have to be optimized if you want to create a good amplifier, and of course you have to also do some sort of optimization if you want to create good lasers. Okay. So, this was about semiconductor optical amplifiers. The last type of semiconductor optical amplifier that I am going to look at is what is called as travelling wave amplifier. Okay. The principles of travelling wave amplifier are slightly difficult and different, we do not want to go into that, but the basic idea is that you do away with the reflections. No, R will not be there, R in fact will be approximately 0. In fact, you can't get R approximately 0. So, what you would actually have is a range of values of R, say from ideal 0 value to about 0.1, let us say, wherein we would treat the semiconductor optical amplifier as travelling wave amplifier, and beyond that we would treat them as Fabry-Perot amplifier. Okay. So, beyond the value of R of say 0.1, 0.12, 0.15, you would deal them as a Fabry-Perot amplifier. The gain of the travelling wave amplifier is actually much smaller compared to the Fabry-Perot design, because there are no cavities here. Cavities serve to have standing modes, and therefore the gain can actually shoot up. So, you are trading off a large gain, okay, in your Fabry-Perot cavity. So, you will have a larger gain here at the appropriate frequencies, and if this is the only frequency of interest that you are working with, then there is no problem. You can easily have multiple channels here within that band, and then you almost all of them will have equal amplification, and you are all very good and very nice. Okay. But if your number of channels actually go around this region, then you are in trouble, because some of the channels will see lesser gain. The travelling wave amplifier overcomes this problem. It gives you almost kind of equal gain frequency dependent. So, this is the travelling wave amplifier, but the gain peak value is actually quite small. Okay. So, you have to of course improve the single pass gain, because that is exactly equal to the gain of a travelling wave amplifier, by continuously changing G, increasing gamma, increasing G, and then reducing this alpha and increasing L. So, this has to be increasing, this has to be increasing, loss has to be reducing, and L has to be increasing, all with certain constraints and approximations. Okay. Even the bandwidth of a travelling wave amplifier, if you were to look at it, will actually be much wider compared to that of the Fabry-Perot cavity. Okay. So, this is the travelling wave amplifier, and this is the overall gain that we talk about. So, the saturation value for the travelling wave amplifier is usually much larger than that of the Fabry-Perot cavity. The big advantage of course is that travelling wave amplifier will never laze, because there is very little feedback that the amplifier is sustaining. On the other hand, Fabry-Perot amplifiers can be made to laze even externally, by actually putting the entire SOA in the middle of a certain cavity and a bigger cavity, and then increasing the feedback of that external cavity. So, SOAs are also used for lasers, not a very good way, but it is also used for lasers, and most importantly SOAs offer high nonlinearity, much higher than the nonlinear fiber nonlinearity, and therefore they are actually excellent for many nonlinear optical signal processing. For example, you can send in two different frequencies into the SOA, and under right conditions you actually end up having 4 different frequencies. Okay. So, you can actually create multiple frequencies by employing the nonlinearity. You can also clean up your input signal by what is called as a phase conjugation. You can improve the data rate by actually putting in an SOA based phase conjugator in the middle of the fiber optic communication link in the form of what is called as a phase conjugation. So, all these advantages that you would get are from the semiconductor optical amplifiers. The downside of semiconductor optical amplifier is that there is a large gain fluctuation, because the lifetime of electrons in the conduction band is about 1 nanosecond. Any bandwidth which is greater than about 1, or any bandwidth which is less than 1 gigahertz will experience severe losses, right, because if you have lesser than 1 nanosecond, then you will or if you have a larger this one, then the smaller lifetime will actually cause the gain pulsations to occur. So, compared to an erbium doped fiber amplifier, the gain pulsations or the gain is very noisy from a semiconductor optical amplifier, and therefore, for this reason it is not used in optical amplification, but it is widely used in other nonlinear signal processing applications that I just mentioned. Okay. There are other differences between semiconductor optical amplifier and erbium doped fiber amplifier. We won't get into these differences at this point, and we close this by saying thank you.